Hi students, today in this session we will discuss about the classification of materials based on magnetism. We can divide the materials into based on three classifications we can have. One is diamagnetic. One is diamagnetic, another is paramagnetic, third is ferromagnetic. So based on the extent of magnetism that occurs in the material, we can classify the materials into these three categories. Clear. So first we will concentrate on diamagnetic material or diamagnetism. So diamagnetic materials. Usually when we apply a magnetic field on a material, two things will happen. Or when we try to magnetize a material, or when we apply a magnetizing field or magnetizing field intensity is applied, that is H is applied, what will happen? Suppose if this is a specimen, if we apply an external magnetic field, means this is nothing but H is not magnetic field, but we are trying to magnetize a material by applying external magnetic field. So what will happen if there are magnetic dipoles, if they are not aligned? After applying this external magnetic field, what will happen? What will happen? They will align in particular direction, and this external magnetic field, that also will be there, and the magnetic field due to internal factor also will be there. So due to H, due to I, and we could say magnetic field, net magnetic field, or the magnetic field in the material is due to that external factor and due to that internal factor. This is what we have studied. Now this is what will happen generally if we try to magnetize a material. This is the first point. Second point is what? Second point is, suppose, say for example, if this is North Pole or this is South Pole, maybe like this, or any other form of any other method, using any other method we are supplying magnetic field. Suppose if we keep the specimen in between this, what will happen? A small amount of objection will be there. If this is North Pole, here North Pole will be induced, here South Pole will be induced. So a small level of opposition will be there. If this is a magnetic field, if there is a magnetic field, a small opposition will be there. This alignment of magnetic dipoles, all this will happen, but other than that, there will be a small opposition to the immediate change that is happening. So this is this objection or this rejection or this opposition we will study using Lenz's law in the chapter electromagnetic induction. Lenz's law we study in electromagnetic induction. Anyway, in short, what I am telling is there will be a small, not much, not big value, but a small opposition will be there. So some small level of magnetic field, a small magnitude of magnetic field will be acting in the opposite direction. Suppose if there are dipoles, all this will alignment, all this will happen, so what also will be there? Material magnetic field will be mu naught into H plus I. All those things will happen. This will happen. Just like in the first case, in the second case also this will happen. But along with this, what also will be there? A small opposition will be there. So first thing is this magnetic field, all those alignment, external magnetic field, internal magnetic field, all those things will be there. That is what is I have written this. Along with that, second thing, the second happening is nothing but a small opposition will be there, which is called the induced magnetic field. This is called the induced magnetic field. Is it clear? Pause the screen and note it down, please. Clear? So what will happen? Suppose if this is a specimen, okay, we are applying external magnetic field, there will be alignment of magnetic dipoles, so what will be there? The magnetic field due to the material will be mu naught into H plus I, and there will be an induced magnetic field. So this is nothing but induced, very small. Okay, this will happen in general cases. Okay, so if this is clear, we will move into diamagnetic material. Okay, so as I said before, in diamagnetic material, a pair of magnetic moment will be there. So net magnetic moment is going to be 0. In diamagnetic material, there is no magnetic moment, okay, because the electron pairs will have magnetic moments in the opposite direction, and net magnetic moment will be 0. So in diamagnetic material, when we try to magnetize this material, there is no dipoles even. So no alignment, no possibility of alignment, but this induced magnetic field in the opposite direction, that will be there. So H will be given, magnetizing field intensity will be given, but there is no possibility of what? Alignment of magnetic fields. Alignment of magnetic dipoles will not be there, but I will be negative here because of this induced magnetic field. We can say the internal magnetic field is due to what? I, due to magnetization. So that will be negative here. Okay, so what will happen? The magnetic field in the material will be mu naught into H plus minus I. Okay, this is what the general formula, but I direction is negative. So we can say that the net magnetic field to a diamagnetic material will be what? H minus I. Clear or what? So there will be a repulsion, a small repulsion will be there in this diamagnetic substances just because of induced magnetic field. Is it clear? Please note it down. Okay, clear? So based on this idea, based on this understanding, we will write the properties of diamagnetic substances. Okay, number one is there are no atomic dipoles. Okay, properties. There are no atomic dipoles in diamagnetic materials. So no alignment of dipoles on the application of external field. So this is the first property. No atomic dipoles, and there is no alignment of dipoles also. Please note it down. Okay, clear? Number two, this induced, okay, there will be induced magnetic dipoles, okay, due to external field. Clear or what? Okay, already we have discussed. Okay, is it clear? Now due to this one, okay, hope you have copied this one. Okay, I am erasing. Okay, pause the screen and note it down, children. So due to this induced magnetic dipoles, due to this one, okay, second point itself, okay, due to this induced magnetic dipoles due to external field, okay, external field will repel the material slightly. Okay, so slight repulsion will be there. Because one field is in this direction, another field is in this direction, but very small value. Okay, so note it down. Okay, so I could say like if this is the direction of applied magnetic field, a small induced magnetic field also will be there. So because of this, a slight repulsion will be there. Okay, clear? Another point is the magnetization I is slightly negative due to induced magnetic field. Slightly negative. Small value, suppose very small value. Why? Because this induced magnetic field, see, this induced magnetic field is the factor associating with the I. So if external magnetic field is there, okay, external magnetic field is there, this is of constant value. Okay, this will not change, but this one will contribute to I. This is very small value and in the opposite direction, so that is why we say this is slightly negative due to induced magnetic field. Is it clear? So this one is H, and we can say, okay, here we can say H will be there, and in the opposite direction, slight, okay, it's very small value of I also will be there. Clear? Okay, done. Next point is, we know about susceptibility. Okay, susceptibility. So susceptibility is also what? Negative. So we know I is equal to what? I is dependent on H. I is dependent on H. This is very less value. This external magnetic field is not affected by any other thing. Okay, induced magnetic field cannot do anything on external magnetic field. This value we are applying. So we are applying this H to magnetize the material. This will not be affected. This is positive. And but I is what? I is negative, very small value. So just because of this reason, zeta is very small value, and it is negative. Zeta is also negative. Okay, say for example, zeta is equal to 10 raised to minus 5. So what is this value? Actually 0.00001. Okay, this is what is zeta is equal to 10 raised to minus 5 means. This value is for copper. Copper is an example for diamagnetic material. Copper is an example for diamagnetic material. Okay, clear? Now suppose if we keep a diamagnetic material in a uniform magnetic field, then we can say this magnetic field lines inside the diamagnetic material will be less dense. Okay, so inside the diamagnetic material, the magnetic field lines will be less dense if we keep it in a uniform magnetic field. Okay, why? Because it will oppose, no? Here this side there is magnetic field in the opposite direction, even small value. So it's because of this opposition, the lines will go in away from the diamagnetic materials. Okay. Okay, clear? Suppose then next point is, in a non-uniform magnetic field, diamagnetic material will tend to move. Okay, diamagnetic material tend to move from stronger field to weaker field. Okay, this is what, say for example, suppose anywhere repulsion will be there. If we keep the diamagnetic material in a external magnetic field, repulsion will be there because of this induced magnetic field. But repulsion from a stronger area will be more compared to weaker field. So it will tend to move from, it will not move, but it has a tendency to move from weaker area to stronger area to weaker area. Okay, because repulsion will be less in weaker area. Okay, that is what weaker field. Okay, clear? Another point is diamagnetic material is not affected by temperature. The properties of diamagnetic material is independent of temperature. We can say the behavior of diamagnetic material is independent of temperature. Okay, because there are no dipoles. What happens if dipoles are there? If we increase the temperature, this dipoles will be disturbed. If we decrease the temperature, dipoles will be aligned. Here dipoles are not there. Dipoles itself not there, so it is not affected by temperature. And susceptibility zeta is not affected with the temperature. Okay, so the susceptibility value is constant. And we know that the susceptibility value is negative also. So its negative value will be constant like this. So this is what susceptibility and temperature curve for diamagnetic materials. Clear? Okay, done. Then next point is relative permeability. So what is relative permeability? Relative permeability is zeta plus 1. It is zeta plus 1. So zeta value is very small, and that is negative also. So for copper I said this is going to be 0.00001. So if zeta, this value plus 1 means this is going to be slightly less than 1. So from this we can say relative permeability is slightly less than 1 in diamagnetic materials. Okay, clear? So some examples of diamagnetic materials are, one is copper I said, then water, mercury, okay, alcohol, hydrogen. Okay, all these are examples for diamagnetic materials. Okay, clear? So the main difference is like nothing but the induced magnetic field against the applied magnetic field. So there is going to be opposition. So field lines will go apart, will go away from it. When we keep it in stronger field, there will be repulsion. When we keep it in weaker field, there will be repulsion. But it tends to move from stronger field to weaker field because repulsion will be comparatively less. Okay, then I is equal to, magnetization is negative, magnetization is negative, so the magnetic field developed will be less than the applied magnetic field. The magnetic field will be what in the material? Mu 0 H minus I, mu 0 H minus I. What is applied magnetic field? What is applied magnetic field? This is going to be mu 0 H. This is in the material, so the magnetic field in the material is less than the magnetic field applied. Okay, this also you can add as a point. Okay, this also you can add as a point. Clear or what? Okay, so just because this I is negative, zeta is also negative, zeta is also negative, and zeta is very small value, and just because of that relative permeability will be slightly less than 1. All are linked, and zeta as well as diamagnetic material property is independent of the temperature. Just because of that we got a straight line in the negative y-axis for zeta temperature graph. Clear or what? Okay, now we will go to paramagnetism. Now we will see about paramagnetic materials. In paramagnetic materials, compared to diamagnetic materials, what is the difference? In diamagnetic materials, atoms with a dipole moment is absent. Okay, but in paramagnetic materials, atoms with a dipole moment are present. So suppose if we consider a paramagnetic material, there will be atoms, okay, with a dipole moment. Okay, so the thing is like net dipole moment is equal to 0. Why? Because dipoles are randomly arranged. Dipoles are randomly arranged. So net magnetic dipole moment is 0. Now what happens if we apply magnetizing field intensity H? If we apply magnetization field intensity H, what will happen? All these magnetic dipoles will align in the direction of magnetic field, and which will contribute what? There will be formation of I. In which direction? In the same direction. In this direction there will be formation of I. So H is also there, I is also there. So what will happen? The magnetic field across the material will become what? Mu 0 plus I plus H. Mu 0 into I plus H. There will be magnetization. So here this was randomly arranged. There was no magnetic effect. Now when we applied magnetizing field intensity on external magnetic field, we got magnetization and there will be magnetic field in the material. So this happens in paramagnetic material. Clear? Please note it down. Okay, so why this is happening? Suppose when there is a magnetic dipole in this direction, when there is magnetic field in this direction, what will happen? This will align this magnetic dipole in the direction of field. So what is the potential energy here? mb cos theta will become 0. Okay, will become negative actually. This will become mb cos theta will become negative. That is stable equilibrium. This will become in stable equilibrium. This will become in stable equilibrium. Correct or what? So minus mb. This will become what? Minus mb, minimum potential energy. So everything will be aligned in this manner. Clear? Okay, so this is possible by lowering the temperature also. If we increase the temperature, In this case also, if we increase the temperatures, these dipoles will be that alignment will be lost. So we can align the magnetic dipole with the two processes. One is by applying external magnetic field and by lowering the temperature. Clear or what? Okay, already we had discussed those 2 points. Once again I am repeating, the magnetic dipoles can be aligned by lowering the temperature and at the same time by applying the magnetic field. Clear or what? Now we will see the properties. Okay, properties of paramagnetic materials. Okay, so number one, the magnetization I is what? Slightly positive. Clear? The magnetization I is slightly positive. And what is the reason for this? Due to the alignment. Okay, due to the alignment of dipoles. So this magnetization is slightly positive, means less value. Not very strong magnetization happens, because this happens due to the alignment of magnetic dipoles, and that value is not very much. Okay, it is slightly positive. Okay, clear? Next point is magnetic susceptibility. Is again slightly positive. In diamagnetic it was slightly negative. Now this is slightly positive here. I is proportional to H, and this is how we wrote what? I is equal to magnetic susceptibility into H. So this I is slightly positive and this is constant. This one we are applying. Due to zeta, very slight positive value, I also will be slightly positive. Say for example, this will be somewhere around say 2.3 into 10 raised to minus 5. The previous case we wrote 10 raised to minus 5 simply for in the case of copper. So this will be positive. Okay, this will be positive. This value I can say this is for aluminium. For aluminium 2.3 into 10 raised to minus 5, very less value but positive. Clear? Please note it down. Clear? Okay, third property is the magnetic field inside the material is greater than the applied magnetic field. Correct or what? Because the magnetic field through the material is going to be mu naught into H plus I. So this is positive this time. Mu 0 H is the external magnetic field. B external is how much? Mu 0 H. B internal is what? Internal is actually mu 0 I. So both of them putting together only what? B material, B net is actually what? B external plus B internal. Since this is positive, the magnetic field through the material is going to be a little bit greater than the external field. That is what this point is. Clear or what? Okay, this I value is less, but everything putting together, this will be a little bit greater than the applied magnetic field. We can say here slightly, we can add here slightly greater than the applied magnetic field. That is the third property. Clear? In the case of diamagnetic, what we said, the magnetic field in the material is slightly less than the external field, okay, the magnetic field through the, because minus I was there. Now here another thing is, suppose if this is north and if this is south, and if we keep a paramagnetic material here, this is a magnetic field line, okay, then another magnetic field line, another magnetic field line here again, this is how. So here the magnetic field lines inside paramagnetic is denser. Magnetic field lines inside paramagnetic material is denser. Okay, denser. Why? Because there is the opposition will be there, but very less opposition. Here also induced magnetic field will be there, but that opposition is very less when we compare to the magnetization I. So this will attract, will go through this. They will try to move like this. See, if this magnetization, if the magnetization I is in this direction, okay, this is a magnet, so this is obviously, this will become north and this will become south. So obviously these lines will have an inclination to move towards this. Suppose in diamagnetic, what will happen? Diamagnetic, this opposition was more, so this was almost like a north pole and like south pole, very small, very weak magnet, very weak magnetic property for dia, for dia. But here opposition is there, even though for diamagnetic also opposition is there, induced magnetic field is there, but I is very much stronger than this. So this is how it is going to be. So if this is a material, this is just like a what? South, north. So obviously the lines will, what will happen? It will try to come through this. Clear or what? Okay, that is the next point. Okay. Another point is, in non-uniform magnetic field, the paramagnetic material tend to move from weaker magnetic field to stronger magnetic field. stronger magnetic field. Okay, why? Because diamagnetic was repulsion. Okay, there was repulsion, but paramagnetic means attraction. So the attraction is more in stronger magnetic field, so it will tend to move from weaker magnetic field to stronger magnetic field, but it doesn't move. It doesn't move, but it will have the temptation or tendency to move from weaker magnetic field to stronger magnetic field. Clear or what? Because paramagnetic means attraction will be there. Attraction will be there. The electric field, the magnetic field property is in what? In the same direction of external magnetic field also. Clear or what? Okay, this is another point. Okay, clear? Another point is relative permeability is what? 1 plus zeta. And this zeta is positive. Zeta is positive. So, and small value. Zeta is positive and small value. So, mu r is slightly greater than 1. Greater than 1. Okay. Mu r is slightly greater than 1. Mu r is slightly greater than 1. Clear? Next point is, okay, I will write here. See, magnetic dipoles are there, aligned magnetic dipoles are there in paramagnetic substances. So that it depends on the temperature. If we increase the temperature, that alignment will be disturbed. So the behavior of paramagnetic substances depends on what? Temperature. So we can say that the behavior of paramagnetic substances depend on temperature. Okay, that is one point. Okay, so just because of this reason also, susceptibility zeta of paramagnetic varies with temperature. Okay, the susceptibility zeta of paramagnetic also varies with temperature. Okay, so how this is related? The susceptibility zeta is inversely proportional to temperature. If temperature increases, susceptibility zeta decreases. How this is? Like I is equal to what? Zeta H. So temperature increases, zeta will be decreased, I also will be decreased, alignment will be lost. So zeta is inversely proportional to temperature. Clear? And we can say the proportionality is nothing but C by T. So this is called Curie's law. This is called Curie's law. Curie's law. Curie's law. This is Curie's constant. Okay, so Curie's constant. C is Curie's constant. This is applicable for paramagnetic material. Okay, please note it down. Clear? Few examples of paramagnetic substances are one is aluminium, chromium, same way copper sulfate, copper is diamagnetic. Copper is diamagnetic. This is copper sulfate. Then oxygen at STP. oxygen at STP. So these are the examples of paramagnetic substances. And one more thing is like suppose if this is temperature and if this is susceptibility, we have seen susceptibility is inversely proportional to what? Temperature, or susceptibility is equal to what? C by T, where this is what? Curie's constant. Curie's constant. So how the graph of susceptibility will be? It will be like this. Okay, susceptibility temperature graph will be like this. Okay, hope you understood. Okay, clear? Now so we have seen diamagnetic substances, paramagnetic substances. Now we will see ferromagnetic substances. Okay. Ferromagnetic substances. Okay, so first point is, just like we have seen for paramagnetic substances, okay, there will be magnetic dipoles present in ferromagnetic substances also. Okay, so there is presence of magnetic dipole moments. Magnetic dipole moments. So that is there. Now next point is, okay, generally in a paramagnetic we know in different directions there were magnetic dipole moments. In ferromagnetic substances we have seen we have to depend on domain theory. What is this? Okay, there are different magnetic dipoles. They interact each other. Okay, it is just like a magnetic dipoles interact each other and they spontaneously align in various small volumes called domain. Okay, so you can read this. Magnetic dipoles interact each other and they spontaneously align in various small volumes called domains in some directions. In domains. Okay, in same directions in domains and different directions outside domain. Okay, I will draw here so that you will understand. Pause the screen and note it down. Okay, so this is just like various domains will be formed. Okay, various domains will be formed. Say for example, okay, so here I am drawing 4 domains. This could be 4, 5, 6, any. Okay, and this is one domain. In this we can see dipoles like this. Okay, here in this domain we can see some dipoles like this. In this domain we can see some dipoles like this. Here we can see some dipoles like this. So various domains will be formed spontaneously. even without applying magnetic field. This is how. But inside domain they will be in same direction, and outside the domain they will be in different directions. Please note it down. Okay, and let me tell you domain size. Domain size will be somewhere 10 raised to minus 12 meter cube, and in one domain how many number of atoms? In one domain 10 raised to 20 atoms will be there. Okay, so they will form domains like this. Okay, they will form domains like this. Okay, now what is the net magnetic moment of this whole thing? Net magnetic moment of this whole thing will be 0, because they have grouped, but all the groups are in different directions, and M net is equal to what? 0. Clear? Okay. Clear? Now what happens when we apply an external magnetic field? When you apply an external magnetic field, okay, while applying external magnetic field, two things happen. Okay, while applying external magnetic field, two things happen. Number one is, okay, domain growth. Number one is domain growth. Okay, which is nothing but some domains will have magnetic dipoles in the direction of applied field, so that domain will grow. Okay, so the domains with magnetic dipoles in the direction of applied field grow in size. Okay, so this is what happens when we apply external magnetic field. One thing. Second thing is what? Domain orientation. Okay, domain orientation. Okay, domain orientation. This is nothing but the magnetic moments okay, moments in other directions from the applied field okay, from the applied field will try to orient or try to align in the direction of applied magnetic field. Okay, so this is what is the second thing that happens. Clear or what? Okay, so while applying the external magnetic field, domain growth also will happen. Okay, sorry, domain growth also will happen. At the same time, domain orientation also will happen. Okay, please note it down. Pause the screen and note it down. Clear? Shall I erase? Okay, say suppose if we consider like this. If in the domains, if the dipole moments are in this direction, okay, let us, okay, fine, no issues. Okay, domain growth means domain growth. Suppose if you are applying magnetic field in this direction, external magnetic field is in this direction, that is H is applied in this direction, then one possibility, that is domain growth, happens like this. Suppose here this domain, here the magnetic dipoles are in the direction of external magnetic field, so that will grow, and all the magnetic dipole moments will all align in the direction of magnetic field. So this process is easy, very fast. Okay, and the other ones which are in this direction, they will start aligning in this direction. Here this was in this direction, so here suppose if we consider, okay, so first let us see this. This is one possibility. This one, other one I will show like this. Okay, so here domain growth, domain orientation. Okay, so that is nothing but, suppose growth of domain will happen on one side, so the other ones, say for example this one, okay, they will start changing its direction. This one will start drifting into that direction, so here this also will start drifting in this direction. Okay, so this is what is domain orientation and domain growth. Hope you are able to understand. Clear? Okay, shall I erase, pause the screen and note it down? Okay, now we will write the properties. Okay, number one, the magnetization I is of large positive value, okay, because of domain growth, because of domain, okay, because of domain growth, this will have large value of magnetization. Okay, clear or what? Okay, so that itself, this domain formation will help in the magnetization process, so I will be of very large value. Then susceptibility, magnetic susceptibility is very large, so magnetic susceptibility, say for example, will be of 10 raised to 3,000 times, something like that. Okay, clear? Number 3, suppose if we keep north pole, south pole, something like this, then if this is a ferromagnetic, then magnetic field lines will very densely closer inside the ferromagnetic materials. Okay, so likewise this will be very dense. Okay, this is of ferromagnetic material, this is what is going to happen. Okay, number 4, in a non-uniform, So this is nothing but if we keep a ferromagnetic material in a uniform magnetic field, all the magnetic field lines maximum will be attracted towards this. This is because very strong I. The I is very strong. Clear or what? So this will be attracted like anything. Okay. So this is south, this is north, and very strong. So maximum it will be attracted. In a non-uniform magnetic field, in a non-uniform magnetic field, okay, a ferromagnetic material moves quickly from weaker field to stronger field. Okay, is it clear? Because previously I said in diamagnetic material will tend to move from stronger field to weaker field because it is repulsion. Tend to move, doesn't move, but tend to move. It has the tendency to move. Paramagnetic materials, they will tend to move. They tend to move from what? Weaker field to stronger field because it is attraction. But here it will quickly move. It will move. Okay, not just tendency. It will move from weaker area to stronger field. Okay, that is another property. Note it down, please. And this relative permeability is equal to what? 1 plus zeta. So this will be large positive value this time. Relative permeability will be much greater than what? Mu r will be much greater than what? That is another property. Okay. And the temperature dependency, since this magnetic dipole alignment dipoles are there, it depends on the temperature. The behavior of ferromagnetic substances depend on temperature. So that dependency will be what? Inversely proportional. If temperature increases, what will happen? When temperature increases, what will happen? This magnetization decreases. Okay, clear? So what will happen to susceptibility? Okay, susceptibility decreases with the increase in temperature. Clear or what? Clear? Okay, so another point is at a transition temperature called Curie's temperature. I'm sorry. Curie's temperature, the properties of ferromagnetic material will become paramagnetic. Okay, so at Curie's temperature, at some high temperature called Curie's temperature, the behavior of ferromagnetic will change into paramagnetic. It will not become paramagnetic material, but the behavior will become paramagnetic like a material. Okay, please note it down. Okay, so here example, 770 degrees Celsius is Curie's temperature for iron. Curie's temperature for iron. Okay, so 770 degrees Celsius is the Curie temperature for iron. So such a thing is there. It is denoted as Curie's temperature is denoted as what? Tc. It is denoted as Tc. Clear? Now based on this we will draw the graph for susceptibility and temperature. Okay, noted. Pause the screen and note it down, children. Now how is the behavior of susceptibility? Susceptibility was a straight line in diamagnetic, that too negative. Then susceptibility was inversely proportional in paramagnetic. In ferromagnetic, okay, susceptibility will be like a zeta temperature. So this will come like this. So at this point, this is nothing but Curie's temperature. So from here onwards, this is going to be just like a paramagnetic. So till this, it will be just like a, here this is having ferromagnetic property. From here onwards, this has paramagnetic nature. Okay, and this Curie's temperature is inversely proportional to T minus Tc. So this is the given temperature. Tc is nothing but the Curie's temperature. Okay, clear? Note it down. Okay, this is called a Curie Weiss law. Curie Weiss law, and susceptibility is equal to C divided by T minus Tc. Okay, and this is applicable, okay, applicable only if the temperature T is greater than Tc. Okay, okay, note it down. So that's all about the classification of materials based on magnetism: diamagnetic material, paramagnetic material, and ferromagnetic material. Okay, so you can see about zeta, susceptibility, and this one, relative permeability. I think we have written that also. Relative permeability, then the zeta temperature graphs for all this. So if you understand and study, okay, just with the reasons we have explained, so hopefully it will be easy for us to remember instead of by hearting, okay, certain things. Okay, students. Okay, then bye bye, good luck. Now related to the magnetism of the materials, we can find a type of loop called hysteresis loop. Okay, hysteresis loop. Hysteresis loop. So this hysteresis loop is a curve. This is a curve between magnetizing field and magnetization vector. Magnetizing field and magnetization vector. That is, in the x-axis we will be giving magnetizing field, and y-axis we deal magnetization vector. That is, suppose inside a solenoid we keep a material. If we keep a material and if we pass current through this, okay, passing current through this, so what will happen? There will be a magnetic field. Okay, so if this is the direction of current, then in this direction magnetic field will be there. In this direction magnetic field will be there, and if we keep a soft iron core inside that solenoid, that will be magnetized. Okay, so that is what we are going to observe here. So suppose if the initially if this doesn't have any magnetization, and we are slowly increasing the magnetizing field. So if H we increased, maybe say 100 dipoles are aligned. So again we are increasing. So when we increased the current, magnetizing field has increased, 100 dipoles are aligned. Again if we are increasing the current, H is further increased, 1000 dipoles are aligned. I increased again, magnetizing field increased again. Now say 1 lakh magnetic dipoles are aligned. Again increasing the current, magnetizing field has increased, maybe 1 crores are aligned. Finally we can say that all the magnetic dipoles are aligned. No more to go. So further I increased, H increased, so no more change here. So increasing we are getting, and finally we got saturated. Okay, is it clear? Okay, so I'll draw better. Okay, let it be like this. Okay, now saturated. So now what we are doing is, so this is the first data. Now what we are going to do, I am erasing this. Maximum saturated, it is completely magnetized. So now what we are going to do, we will decrease this current. So H also will decrease. So what will happen? I also will decrease. So we have started decreasing this. I is decreased, H is decreased, I is also decreasing. So maximum we have made current is equal to what? 0. So again H what happened to H? H becomes 0, but I is not equal to 0. So we have decreased this, and finally what happens is, this is now IH became 0, but still I is not 0. Okay, because when we applied magnetizing field, dipoles got aligned, all the dipoles are aligned. Now when we remove that H, some dipoles got realignment, they got shuffled, they directed in random directions and all, but at least some percentage of dipoles will be still in the same previous direction. So that is why I is now this much value is there. Okay, this much value is there. So you can remember, so this much I is still there. This much I is still there even after making the value of H0. Okay, so let us mark this point O, say A, let us call this B. Now even after making the current 0, magnetizing field 0, I is not 0. I means this magnetization vector is still not 0. Now what we are doing? Now somehow we need to make it into 0. I will have to make it 0. So what we are doing is we changed the direction of current. Changed the direction of current. Changed the direction of current. When we change the direction of current, then magnetizing field, okay, or magnetizing field intensity will change its direction. So now we will start magnetizing the material in the reverse direction. So what will happen? Again I will decrease. Alignment of the dipoles will start aligning in the opposite direction. So finally what will happen? This will come and finally I will become 0. I will become 0. I will become 0. I will become 0. Okay. Now again, same way, I increased, H increased, I became 0. Now if we keep on increasing I and H, what will happen? This will start, H is increasing in the reverse direction. So what will happen? This I will start increasing. So I also will increase. Again I increases, H increases, I becomes what? Saturation. Because the magnetizing happens in the opposite direction. Finally what will happen? Here also this will get saturated. Now what we will do? We will start decreasing current. H also will be decreased, I also will be decreased. Finally again in the same way, what will happen? This I will not become 0. Further reduction of I, H, but magnetization will not become 0. Okay, so even after H is equal to 0, so H is 0 now, still what? This magnetization is not 0. Still some dipoles are aligned in the opposite direction. Okay, now what we can do? So current is in the opposite direction. So H was also what? Minus H direction. Now what we will do? Again we will change the direction of current. Again what we will do? Again we will change the direction of current. We will increase I, we will increase H. So what will happen? So slowly this I will start increasing. Finally, just like the previous case, I will increase. Again current will be increased, magnetizing field will be increased, magnetization will be increased, increase, I will become what? Saturation. Okay, so this is what is hysteresis loop. First we went like this, came like this. Okay, so this is what? O, A, B, C, D, E, okay, A, likewise. So now here these 2 points I am marking. I shall give notes for that. First you note it down. Okay, now OB is called coercivity. OB is called coercivity. What is coercivity? The ability to retain that magnetization even after the removal of magnetizing field. Okay, the ability to retain magnetization. Magnetization is what? Magnetic property, ability to retain that magnetic property even after the removal of magnetization is what actually I vector, even after the removal of magnetizing field H. Clear or what? So that is what is coercivity. Okay, coercivity. Clear? Fine. Now suppose if I put A, B, C, D, E, okay, let me put here F. Okay, O, F. Okay, shall I erase this part? OF. OF is nothing but retentivity. This is coercivity, this is retentivity. Okay, so this is nothing but how much magnetizing intensity is to be applied in order to make the magnetization to zero. Okay, how much magnetizing field that is H is required to make the magnetization to zero. Okay, so one is retentivity and other is coercivity. Okay, note it down. Pause the screen and note it down. Clear? Done? Okay. So to make a permanent magnet, this retentivity and coercivity is having coercivity, more coercivity, and retentivity is preferable. Okay, for permanent magnets, for making permanent magnets, it is preferable to have more coercivity and retentivity. Okay, so that we should keep it in mind. Okay, so if question is asked, then for making permanent magnet we should have more coercivity, more retentivity, means this loop should be bigger one. The loop should be bigger one. Clear? Now you can see here, for same value of H, I have three values of I. So this is H, we have I. Okay, so for same value of H we have I1, I2 and I3. That is for same value of H we get three values of I. Means how much magnetization will happen, that it depends on the history of the material also. Okay, so magnetization depends on the history of material, okay, how much it is magnetized already, all those things will have the decision in deciding the magnetization. Clear or what? Note down all these points. Okay. And this area of the loop area of the loop is equal to the wastage of energy in a cycle. Okay, so the area of the loop is nothing but the wastage of energy in a cycle. And this hysteresis loop we study for paramagnet. Okay, we study for paramagnet. Okay, please note it down. I'm sorry, here I wrote paramagnet. This is ferromagnet. This is a property of ferromagnet because we make permanent magnet using ferromagnet, not with the paramagnet. Okay, ferromagnet is having the more magnetization property, the domain, all these things. So the best magnet, okay, for making permanent magnets and all are ferromagnet. Okay, so I'm sorry, this is not para, this is ferro. Okay, is it clear all of you? Okay, so this is all about hysteresis loop. This is also we need to understand in all these points. Okay students, thank you, goodbye, good luck.